In this section, we are going to solve maybe one of the most challenging and interesting problems on computer vision for quite some time now, the real-time object detection. At first, we will become familiar with the object localization problem and how to label the data and slightly modify the neural network prediction layer to fit this kind of a new problem. Next, we'll solve the object detection using the classical sliding window technique. And in the end, we will explore some of the downsides of using such method. Then we will walk through the internals of the convolution sliding window, together with some insight on how this method efficiently addresses the downsides of the classical sliding window solution. Continuing further with the state-of-the-art algorithm, You Look Only Once. Although YOLO does really a great job so far to detect objects fast and reliable, there are still two more problems and solutions to meet. In the end, we will see how to build a Java real-time object detection application for detecting cars, pedestrians, traffic lights, bicycles, and so on. And in addition, we'll run the demo live with different videos. Resolving object localization problem. In this video, we will visit a quite interesting problem to solve: the object localization and detection. In addition, we will see how to label the data and modify the prediction layer in order to fit the object localization problem nature. In the end, we will extend the same idea for landmark detection, which will enable us to do even more fascinating things, like detecting the person's smile. We are already familiar with the image classification problem, where we have an image and we want to predict if that image represents or contains any of the desired classes, like is this a car, is this a person, and so on. Now, beside image recognition, we want also the object position in regards to the image. So maybe we want the object to be marked with a bounding box like this. And this is the object localization, which we will solve during this video. Extending the idea to multiple objects leads us to the object detection, which we will see in more details in the next video. By now it is clear that in comparison to the image recognition, where the labeling of the data, it was quite simple. So you go into the images and you say, is this image of this class or not? So is this image a car? Yes, so put 1. If not, then put 0 there, because this image does not have any of the cars. For the object localization, the labeling of the data is quite more intensive and difficult to do because we have more information. So let's see more closely how we can handle that. So we have a PC variable which simply denotes the fact that does this image has any of the classes we want to predict or not. 1, it means that we have one of the classes we want to predict, and 0, no, we don't have any of them. Bx and by, they mark the center of the bounding box. Then bh and bwidth, the edges, so basically the height and the width of the bounding box. Then we have the class number, which is quite similar to the image classifier. In this case, is a car. But in practice, we have many classes, so we can have a bike, a person, and motorcycle we want to detect as well. Before seeing an example, let's denote as well 0, 0, the coordinate of the top left corner, and 1, 1, the bottom right corner. Then one of the examples may look like this. So we have the PC1, signaling the fact that we have one of the classes in this image. 0.5 and 0.5 are the coordinates of the center, because it happens the center of the bounding box is also the center of the image. Then we have 0.5 for the height, because maybe this is like 40% of the all height. 0.8 for the width, because maybe this is like 80% of the all width of the image. And then 1, because this is a car, so just the first class, and 0 for the other classes. Another example may look like this. So we have 0 the PC, and what happens now is that we simply don't care about the other values. We are simply ignoring them. Once the labeling of the data is changed, we clearly need to adapt also the prediction layer. If we take the image classifier example, we have the labeling as we saw in the previous slide. So just we go through the images and say this is the 4th class, this is the 3rd, this is the 0, the 1. And that translates for the 3rd one 0010, for the 4th 0001, so we put 1 on the last place. for the 0 we put on the first place, and so on. And then we feed all this information to a neural network, which through a prediction layer that uses a softmax outputs probabilities for each of the classes. So if we take this example, the neural network may output like 65% this is the 0 class, 50% this is the first class, and so on. And during the training, what happens is that we calculate the difference between the predicted values and the real values we know from the labeling of the data. And then we feed this information to backpropagate step in order to change the weights in such a way that the next prediction will be better. So maybe the next prediction will produce like 85%, this is the 0 class, and these values will tend to go to 0 as they are in the label format. And this will tend to go to 1, of course. Now the case with the localization problem is quite similar. We just have different structure of the data. So the labeling here looks like this, as we saw in the previous slide. So we have the PC, then the bounding box properties, and the class number, which looks identical to the classifier problem. Now it's not surprised that also the prediction layer has to produce the same structure of the data. So the PC maybe here is a bit different because it is a probability, but that can be solved quite easily. We say that values greater than 0.5 are treated as 1 and those less than 0.5 are treated as a 0. And in the prediction layer we have the bounding box properties and then the class numbers. And what we do is quite similar to the classifier problem, so we calculate the difference between each of these values. So if we take the 0 example, we calculate the difference between the center, so 0.22 with a 0.3 and so on. And then we use that feedback to feed the backpropagation step to change the weights in such a way then the next difference will be smaller. So maybe next time this 0.57 will be like 0.65, so more close to 0.7, and maybe the 0.9 will be shrinked to 0.8, so more close to 0.7, and so on. Till now we have enriched the data with more information like the bounding box center, the height, the width, and so on. And by providing more information to the neural network, we also get more information when the neural network predicts. So in a way, the network has become more smarter. So basically we can use the same idea, but we can label the data with even more information. So for the face example, we can have points on some parts that we find crucial, like the eyes and the mouth, like this. So each of these points will be localized by the x coordinate and the epsilon coordinate. Then the neural network will be able to give us this information for unseen faces. So the labeling may look like this. So we have the PC, 1 or 0, denoting the fact that is this a face or not. Then we have landmark 1, x epsilon, that could be this point. Landmark 2, x epsilon, could be this point, and maybe until we reach the 25 points here. Now, by looking at the shapes, we can figure out things like, is this person smiling? Is it serious? Is it angry? And so on. And by having that information, we can do funny manipulation of the faces by putting a crown here, a hat, or maybe other funny things, which a lot of apps nowadays are already doing it.